All right, welcome grade 10 and grade 11 physics students. And the first thing that we're looking at is understanding how to take measurements in physics. A big part of physics is learning how to observe the universe and, more importantly, to be able to communicate our measurements in physics. Okay, it'd be very difficult to repeat people's experiments around the world if we didn't have a common way of describing our measurements. Okay, so what you would have done in your reading is you would have learned a little bit about our common measurements that we've decided upon called SI units. Okay, and then another thing that we need to be able to do is understand how to use common metric multipliers such as kilo or giga. Okay, how do we apply that to SI units in order to be able to do unit conversions? And that's what we're going to be doing in today's little lessons. Okay, so first of all, one activity we did is we tried to measure the amount of gumballs in a gumball machine without having any measurements at all. And what you guys found out is that we can use a gumball as a unit of measurement and find the volume of that entire gumball machine in terms of gumball units. So why can't we use gumballs as a way of measuring distance around the world? Well, the first thing that we need to think about are gumballs universal? Are gumballs in China the same size as gumballs in the United States or in Ghana? Probably not. Can we even if they were, would we trust that people can manufacture them to be the same size? Would there be slight differences? How do we find a standard way of making gumballs so that they're all exactly the same size? And the last thing that we need to think about when anyone designed units of measurement, they need to be convenient to describe the world around us. The world around us is a lot larger than gumballs. So when people designed the unit of measurement such as a meter, we're trying to use a meter as a very convenient tool to describe what is around us, okay, the size of a human. So if I measured my height in terms of gumballs, it would take me a very long time to stack the gumballs in order to get the height, and then I'd have to count them. It would be a very frustrating day if I had to measure everything in terms of gumballs. Okay, so that's how, gives you a little bit of the logic of how our SI units were developed. Okay, a little bit of convenience and a good way of finding a universal system that people can describe those units around the world. Okay, we have ways of manufacturing tools that can be accurate around the world. Okay, so here are our standard units of measurement. For length, you would have read that 1 meter is the unit. Okay, and we'll talk a little bit about how we discovered these units a little bit later on, but the abbreviation is M. For mass in physics, we use the kilogram, not the gram, kilogram. So the kilogram is the unit of measurement, the standard unit of measurement. Okay, and this confuses a lot of students, especially physics students that were last year in grade 10, would often not use the right unit of mass in equations. Mass in equations is always in kilograms. We always have to convert things into kilograms. Time is seconds, not hours, not days. Okay, the amount of a substance, when we're talking about matter, the unit is the mole. Okay, maybe some of you in chemistry last year would have discovered the mole. I know we talked about it in thermal in grade 10. The mole is our standard unit of measuring the amount of molecules in a material. And 1 mole would be equal to let's change the color here. 1 mole would be 6.02 times 10 to the 23 of a substance. That's a very large number, but that's 1 mole. Okay, and temperature, the absolute temperature scale is not Celsius or Fahrenheit. The absolute temperature scale in physics is Kelvin, which we're going to learn about a little bit later. And an electric current is a unit of measurement. Okay, an ampere, amps, how many amps are going into your circuits, that's a unit of measurement. And something that if you're looking at brightness of light bulbs or things like that, the candela is the standard unit of measurement. Okay, so scientists around the world have been discussing this for many times. What you would notice is that in the United States and England, they use different units of measurement. They use the imperial system, miles, they use inches. Okay, that's when I'm trying to describe length. All right, and why is it that the rest of the world doesn't use miles and inches? Well, it's not convenient. Okay, we've come together and described ways of measuring something accurately. Okay, we have better ways of measuring length in terms of meters accurately. We come up with definitions for that. We have better ways of describing mass. Instead of pounds, we found a better system that can be designed universally using the density of materials, or now they've even changed the definition. It's related to Planck's constant. But here you have a picture of somebody, a scientist, who has developed the perfect kilogram, okay, based on the density of a material. Notice that he's wearing gloves. If I'm going to create a standard that everyone can base their measurements from, it's going to be perfect, but if I put fingerprints on that, it's no longer a kilogram. So once he's made that, that's going to go in a chamber that has no oxygen, okay, it's in a vacuum, and then that would be stored. And if I wanted to make a perfect kilogram, I would have to weigh my object in relationship to that perfect kilogram. It's very, very challenging stuff. So scientists will meet once a year to describe the definitions of their SI units. Okay, and one question they ask is, how can I make a tool that would be able to measure this? And how can that tool be extremely accurate? And they always argue about how to find a way to find the perfect second, or the perfect kilogram, or the perfect meter. Okay, but now you know the 7 base SI units. All of physics is based on these units and the combinations of these units. So let's take a look at something else. Okay, well, here's just another SI wheel showing the symbols, the kilogram, the meter. And then we can define these using different variables, which we're going to talk about in this course. Okay, so for example, time is defined by the speed of light. I use the speed of light, the change in the speed of light, to define what time is. Okay, for my amperes, I use electrons, the charge of electrons. For moles, this is Avogadro's number, like I just presented. And for kilograms, it's Planck's constant. That's the most up-to-date way of defining how these units of measurements have been decided. Okay, but the next thing that we need to look at is there are vast ranges of scales and measurements. Okay, so the meter, for example, the length, the meter, is good to describe the world that I'm in right now. Mostly everything I'm looking at around me is meters, okay? But what I do know in the world of physics is that a bacteria is not a meter, a virus is not a meter, the universe is not a meter, it's a lot more than that. So even though the base of distance is meters, we have abbreviations, we have prefixes, we have ranges and scales that we add to that to make it easier to describe. Okay, instead of saying a billion, billion, billion meters, okay, we will find a prefix, a gigameter or a megameter or a kilometer, which you're used to, okay, which helps me describe distances. Okay, everyone knows what a kilometer means, or a kilometer. 1 kilometer is equal to 1,000 meters, okay, and we're pretty comfortable with that. But have you ever heard anyone say, I walked a gigameter today? Okay, or I walked a nanometer? That would be really hard to walk a nanometer, just as hard as it is to walk a gigameter, okay? But rather than trying to describe exactly how many meters you would use, okay, you would put these prefixes in it, okay? So students who are beginning physics have not heard gigameter or megameter or pico or femto, okay? I remember when I started, I didn't hear these things. So what you're given in your data booklet is a table, and it's very easy to use this table to convert what that means. If somebody says you have a gigameter, you look at this table and you see, oh, a gigameter is 10 to the 9 meters. So I take whatever they put in front. If I had 5 gigameters, I would just say 5 times 10 to the 9 meters. So it's quite easy to convert things around. Okay, and in a lot of the course, in this course, we study all the way down to the structure of the atom, which is on the nano, pico, and level, to the size of the universe, which we're talking giga and mega. So you're going to be very used to interconverting these terms, and you're going to get used to using these prefixes. Okay, so let's just take a look. Okay, the average size of a human, the scale of the human is on meters. Okay, and would roughly be around 1.8 meters, let's say. Okay, the scale of the coronavirus, okay, our big bad guy. How many meters do you think a coronavirus would be? Well, the coronavirus is 120 nanometers. So how would I convert that into meters? If I look at nanometers, let's go back to this table. N, okay, is nano. Okay, so a nanometer is 10 to the minus 9 meters. So that's going to be equal to 120 times 10 to the minus 9 meters. okay? And if I want to convert that into better scientific notation, like your teachers have practiced, it's going to be 1.20. Now, what am I going to do to the 10 to the minus 9? It's no longer 10 to the minus 9. If I've moved that decimal place over, it's now 1.20 times 10 to the minus 7 meters, okay? I want you guys to think about that. This is applying your math skills that you've practiced since grade 8 or grade 9 when you've been exploring scientific notation. Try to understand why 120 times 10 to the minus 9 meters is equal to 1.20 times 10 to the minus 7 meters. Did I do that correctly? Okay, and see if you can do that for yourself. It's a good checkpoint, okay? Then, if I look carefully inside of the coronavirus, okay, the coronavirus has RNA, it's got proteins. This is what we're trying to make our vaccines against, that spike protein. What's the size of that guy? Okay, well, if I look at the diameter of the protein, or if I look at the diameter of the RNA, now we're talking 6 nanometers. Okay, so 6 nanometers is equal to 6 times 10 to the minus 9 meters. Okay, and that's how I would put that into regular SI units. And now let's talk about something much bigger. Okay, what about the distance of the universe? What about from the center of the sun to the center of the earth? How many meters is that? Is that nanometers? Is that micrometers? Is that gigameters? Okay, well, let's take a look. I remember there was a song that I learned from one of my favorite bands that said that the distance between the sun and the earth is around 90 million miles. Okay, that's from a song that I learned from They Might Be Giants. I really love that song. Okay, so it's 90 million miles away. Now, I'm Canadian and I've never learned miles. Okay, I learned meters and kilometers. But the people that made that song are American, so 90 million miles away. How would I convert that into something that I know, which is meters? Okay, well, we have to do some systems of conversions, and that's what we're going to be talking about next. How do I convert one type of unit into another type of unit? So 90 million miles, I know that 1 mile is equal to 1.6 kilometers, roughly, okay? So in order to convert miles into kilometers, I'm going to try to do something like this. 90 million miles times 1.6 kilometers per mile. Okay, the miles will cancel out, leaving me kilometers. And I'm going to have around 150, just erase this, 150 million kilometers in the end, okay? Now, what I just demonstrated for you is a concept that is very, very important in science and unit conversion. We like to write down all our units so that we can keep track of it. And I want you to ask yourself, does this work out? Would miles cancel out in that fraction form when you multiply miles over 1 times kilometers over mile? Would those units cancel out? Okay, and this is a principle called unit cancellation. Okay, that's a good way of doing unit conversions. So 150 million kilometers, but that's not meters, that's not SI units. How do I convert that into meters? Okay, so I know that 1 kilometer is equal to 1,000 meters. So I would have to multiply that number by 1,000. Okay, and I'm going to show you that through my unit conversion techniques. Okay, so if I multiply that by 1,000 meters per kilometer, the kilometers cancel out, and I'll be left with meters, and that gives me 150. Wow, I got a lot of numbers. I'm running out of space. Okay, and that's why scientists use scientific notation. That's too many numbers, and it's just going to take me too long to do my homework if I use those numbers. So I can write that as 1.5 times 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Or I can write that as 150. Now there's 9 zeros, 1, 2, 3, 4, 5, 6, 7, 8, 9. If I go up to this table, 10 to the 9 is giga, okay? So then what we can say is I have 150 gigameters, okay? That's the logic behind why we have those identifiers and why we use scientific notation. So again, scientific notation just prevents me from writing a bunch of numbers on a piece of paper and running out of space. And these modifiers over here just allow me to prevent me from saying 1.5 times 10 to the 11. That would sound very strange in English. It's easier for me to say 150 gigameters, and people can do that conversion in their head. Okay, so let's do a few practice conversions. At any time in these videos, you can pause, okay, take a break, come back, or answer some questions on your own, make some notes. You don't have to follow the whole thing. Okay, so this morning I ran 3 miles. How many meters did I run? Okay, so again, there are 1.6 kilometers in 1 mile. Okay, I need to know that conversion. Okay, so then 3 miles times 1.6 kilometers per mile is going to be roughly around 4.8 kilometers. And if I want to find meters, I got to do another conversion, which is times 1,000 meters per kilometer. Okay, that cancels out, giving me 4,800 meters. Okay, notice that when I'm doing physics, I put a box around my answer all the time when I finally finish it. It allows me to, and I like to write everything in a line so I can work backwards to make sure everything is done correctly. If the units cancel out and give me what I want, I know I've done it correctly. Okay, now a bacteria has a diameter of 18 micrometers. How many bacteria can be lined head to tail in 1 meter? Okay, so 1 bacteria is equal to 18 times 10 to the minus 6 meters. How do I know that? Okay, if I go up to this table, micro is 10 to the minus 6. So 1 bacteria is 18 times 10 to the minus 6 meters. So how many of them would fit into a meter? Okay, so then what I can do is I would have 1 bacteria over 18 times 10 to the minus 6 meters, okay? So that means 1 bacteria per 18 micrometers, okay? And if I multiplied by a meter, okay, the meters are going to cancel out, and it would leave me with the unit bacteria, okay? Now, what does this mean when I'm taking 1 divided by 18 times 10 to the minus 6 times 1? Okay, that's just, I have to do the inverse of that number. So this formula that I've created is telling me that I have to take the number 1 and divide it by 18 times 10 to the minus 6. So if I quickly do that in my calculator, which is not prepared, okay, let's see here. 1 divided by 18 times 10 to the minus 6 is going to be equal to 55,556 bacteria, or 5.6 times 10 to the 4 bacteria, or I can say 56 kilo bacteria. Why not? I don't think that's an actual unit, but just getting you to think about terms like that. Okay, now the average human reaction time is 250 milliseconds. What's the human reaction time in seconds? So I need to think about, how do I convert milliseconds into seconds? Okay, I can do that quickly by looking at the table. So a millisecond, milli is 10 to the minus 3. So if I want to convert that into seconds, okay, I would just have to say 1 millisecond. So 1 millisecond is equal to 1 times 10 to the minus 3 seconds. So in order to convert 250 milliseconds, so 250 milliseconds times 1 times 10 to the minus 3 seconds per 1 millisecond, that cancels out, would leave me with 0.25 seconds. Okay, and the last thing that I want to work on is something that relates to our homework, okay, where you have to do a little bit of research. The mass of a single hydrogen atom is 1.0078 atomic mass units, okay? I need to figure out what is an atomic mass unit. That's in the periodic table. If you look at the periodic table of elements, you'd see that number underneath each element. And I want you to calculate the number of atoms contained in 1 kilogram of hydrogen. So first of all, I need to look at an atomic mass unit and know what it means in terms of kilograms. So 1 U, or atomic mass unit, is equal to, and I did some research on Google, 1.66 times 10 to the minus 27 kilograms. Okay, so that means that 1 hydrogen atom is equal to 1.0078 U times 1.66 times 10 to the minus 27 kilograms per U. And the U's will cancel out. And that is equal to, getting on the calculator, you guys can follow along. Okay, so 1.0078 times 1.66 E, that gives me 1.67 times 10 to the minus 27 kilograms, okay, for 1 hydrogen atom. So how do I find out how many hydrogen atoms are in a kilogram? Okay, so 1 hydrogen atom per 1.67 times 10 to the minus 27 kilograms times 1 kilogram. That way my kilograms cancel out and leave me in the units of atoms, like we did with the bacteria. So my units now are atoms. Okay, so then this formula that I've created is telling me to take 1 divided by that number, and that should give me the answer. So let's quickly do that. And I'm left with, a big number, 5.98 times 10 to the 26 atoms. I don't even know what prefix that is. That's a huge, huge number. That's like a billion times a billion times a billion, almost a billion, right? So times a million, all right? So that's a lot, okay? 100 million, that's a big number. Okay, so 5.98 times 10 to the 26 atoms. And that would explain why maybe we use the term moles to describe atoms rather than those giant numbers. Okay, that's our first little lesson for today. We're going to do some homework to practice doing these conversions and using SI units. All right, that'll take us about a week of time, and I hope that this video was a little bit helpful for you.